Okay, here's week 10. Do a little bit of an introduction here. We're talking about oscillating support. So basically, this is section 3.5. Basically, what we're talking about is that now instead of placing a forcing force onto the degree of freedom mass, we're now going to move the base in this manner right here. Right, so we will do a oscillating motion in there. The result of an FBD IBD is of this form right here, where we have the difference between the motion and the amount of force being placed onto there. This isn't too different from some of the previous sections in the book. That does have a little bit of difference in some respects, but not a lot. We have the same type of treatment in order to get to this result right here. We basically assume a form of y is equal to large Y sine of omega f times t is being applied into there, and then we can take the derivatives of these and plug them back into this and end up with an equation of motion where we can eventually find a relationship like this right here. And this is not too much different from transmissibility, except it isn't transmissibility. You can reduce this nicely into a compact form, and it looks a lot like stuff that we've used before. Now, down here, I copied and pasted something from Dr. Jasinski's notes. And then when I went back to look and try to figure out, like, okay, well, how did we get to this step? I was a little flummoxed, and I think that actually came out in class. So allow me to explain briefly without causing too much additional headache. All right, so we have this X up in this top form up here. But if someone asked you, okay, this is the position transmissibility, but what would be the force transmitted? Okay, so this is a little bit different from our previous usage of like transmissibility in forces, because before we had a force like an FO times sine of omega t that was being applied to the thing. Now we just had motion at the bottom, and if someone wants to know what is the force that's there at the transition, let's see, between the springs and the damper and the base that are being moved. Well, that still becomes F equals ma onto this right here. So we would have, and we have mass times acceleration of the thing moving. So we could replace that acceleration with capital X omega f squared, and let's call it ft right there. Okay, so this is the ft right here, and so we can, if we want to continue with what we have up above, right, we'll take that x and we'll rewrite this out here. We'll replace that x with these other parts, and then start to do some manipulation. Another thing we'll note is that we have some mass now that we didn't have before. So just as a variable, let's say, we did have the mass before, but when playing around with this, we could say that the x was equal to ft divided by m and omega f squared. And then we could also take some k's and put them in here, right? And with that, we could recognize that right there is omega n squared. So now we're dealing with ft over omega n squared over omega f squared, and then we still have a k remaining right in there. So we note that that's r squared. So maybe we want to write that out again. That x that we were replacing before has all of a sudden become ft r squared over k, right? So now you can see that if we move all this stuff, replace this x right here, then we hit that ft, and then we get we have our y, there's a k times it, and then there's the other r squared. So that's how we got to this position, right? I didn't do a very good job overall, I think, of explaining that, but there's still, I think you can see that this is the transmitted force due to base motion. And what's a little interesting, okay, so this is from another book, reinforces that that is a correct thing. What's really interesting to me is how large these two things become compared to each other as we go upwards with this. But once again, remember that this is a ratio of the transmitted force divided by the stiffness of the spring and divided by the amount of the magnitude of the base motion. So it can end up getting pretty loud. And this can also be related to the rotating unbalance as well. They show that this has these follow in the same trend. All right, so I'm going to start another video for this one. I'm not really proud of this work, but I did my best to try to explain these equations without driving them.